Welcome back. So we're going to continue moving forward from arc length and space, and we're going to talk about the unit tangent vector. And this is going to come into play as we start talking about curvature as well as torsion, building towards using acceleration as well. So one thing that we already know is the velocity vector v is the derivative of our position vector with respect to t. And the velocity vector is going to be tangent, right? Because the derivative is tangent to that position curve. And so then we'll call t, capital T, this is a vector, is the unit tangent vector. So it's the tangent vector equal to 1. If it's a unit vector, it's really just telling us direction. And the way we find the tangent unit vector is we take that velocity vector and divide it by its magnitude, the same way we find any unit vector. So since the vector for velocity is tangent to the curve, this unit vector, which also has the same direction, it's just 1 unit long, is also tangent to our smooth curve C at some point R. So remember that position vector R extends from the origin to a point on the curve, and then V is this longer red line. That's my tangent vector, the derivative of R, and the derivative of R is velocity. So let's just do one quick example where we make sure we know how to find the unit tangent vector. So in order to find the tangent vector, remember tangent or that slope of the tangent line is coming from the derivative. So the derivative of position is velocity. Here, I'm going to find the velocity of r. 1 plus 3 cosine t is just going to be negative 3 sine t I. 3 sine t, that derivative is 3 cosine t j. And then I've got 2t k. So as I said, this is the derivative of r with respect to t. Now that tells us the tangent vector. We need the unit tangent vector, which means we need to take this v vector and divide it by its magnitude. So the magnitude of v is the square root of negative 3 sine t squared plus 3 cosine t squared plus 2t squared, or the square root of 9 sine squared t plus 9 cosine squared t plus 4t squared. Factoring the 9 out of both of these, that leaves me with 9 times sine squared plus cosine squared, which is equal to 1. So I'll simplify this and just write 9 plus 4t squared. And that represents the magnitude of my velocity vector, which is tangent to my position vector. Therefore, that unit tangent vector, t, capital T with a vector line above it, is v divided by the magnitude of vector v, or negative 3 sine t I plus 3 cosine t j plus 2t k divided by that magnitude, the square root of 9 plus 4t squared. And I don't know that it's necessarily important to do that here, but the computer may ask you to. So, if we wanted to clean up those components and have them each written individually, we should technically write 3 sine t over the square root of 9 plus 4t times my I plus 3 cosine t over the square root of 9 plus 4t squared, I left a square off over there, times j plus 2t, over the square root of 9 plus 4t squared. Okay. And that represents our tangent unit vector. So this vector is 1 unit long, but it is in the same direction as our tangent vector. And as I said, when we start talking more about the motions of these curvatures and the torsion, we're going to have 3 unit vectors that we use a lot. We'll have our tangent unit vector, our normal unit vector, and then we'll also talk about B, our binormal unit vector. But we're getting to that. You just need to make sure you know how to find a tangent unit vector.